The notes for everything up to this is all ready, and they'll send it out fairly soon. I'll send it to you, and you can send it out here. Okay. Okay. What I want to move on to next is, now that we've defined notions of fairness, what can we do? Because that's really the game here, right? So in other words, we'll move from definitions to mechanisms. In other words, algorithms. How do we make algorithms that will help us do learning, but also maintain fairness under some of the definitions we've seen so far? Okay? And of course, we've seen many definitions. I think by my count, we've seen 5 different definitions of fairness. So it'll be too much to expect that a single algorithm can ensure all of these things. In fact, as we've talked about, some of these might be in conflict with each other. So typically, you're going to have, okay, here's my definition of fairness. Here's a mechanism that allows me to do learning with this definition of fairness. And even what kind of learning I'm doing, am I doing supervised, unsupervised, it gets very complicated. So I'm going to talk about specific examples of problems, specific examples of definitions, but I'll try to cover all the different definitions we've seen so you get some idea of how you might ensure fairness in these different settings. Like if you have a bandit setting, how do you ensure fairness? If you have this individual fairness type definition, how do you ensure fairness? Things like that. And it would be nice, of course, if there were some general principles that we could use. And it turns out there are some. They're kind of good guidelines. So if tomorrow you had to come up with your own algorithm for maintaining fairness in some system, you could use this as a rough rubric to try and design your process. And so there are basically 3 different ways you can think about trying to ensure fairness in a set of batch mode setting. So let me just draw a picture of what your typical batch mode setting looks like. Again, so you have your data, your training data. This is used to build a model, which is then tested, and then this might go around for a while. Right? This is how you build a model. Okay. What are the things you think one could do to end up with a result that is a good learner, but also is fair under some definition of that? At a high level, what are the kind of strategies you think might work here? So you're saying look at the data, see if there's bias in the data in some way, and fix it, and then what do you do? With what? Just normal modeling. Okay. So a strategy that appears to be being proposed is check if data has bias, fix it, and continue. Okay. Any other strategies?
Well, while evolving our system, we need to check the data we are feeding back.
So let's pretend we're not, so when I did this, I didn't mean the data's feeding back, I just mean I'm training the model. So let's assume it's a batch mode, so there's no feedback problem yet. So in that case, what would you suggest? Just train it blindly on the data, as is.
Yeah, then like tweak it to iterate it to that like the fairness parameters, unfairness value.
So in the break, I was talking to some of you, and we were continuing to argue about this issue, and I came up with a little diagram that I think might be helpful to understand what's going on. There seem to be two conflicting, or potentially conflicting issues going on here. So we have data. Let us describe two potential properties of our data. One is data is ground truth. One is data is unbiased. These are independent properties. And so any possible combination of the truth value of these things can happen. So let's write them down. So they might both be false. Okay, these are the four possible situations with your data. Of course, I'm simplifying the problem maybe a bit too much, but it's just a thought experiment. Let's just rule out some obvious cases, right? So if your data is not ground truth and it's not unbiased, then why are we wasting time with it? So this is a case as our data is crap. We don't need to worry about this. Most machine learning assumes that we sit here. It's ground truth, it's unbiased, everything's good. Nothing to worry about. Let's move on. Let's just build our code. The problems I'm talking about today, right? Or we talked about all this course long, is when you might have this. How many of you have heard of this example of Microsoft's chatbot? Microsoft put out this chatbot on the web called Tay, and the idea was that it would learn to talk to people. Did any of you hear about this? You heard about this? Okay. Anyone else? Okay. So the idea was Microsoft said, okay, we have this chatbot. We'll put it on the web. You can basically go to a web page and sort of type things at it, and it'll talk to you. And as it talks to you, it will learn. And it will learn how to talk to you better. So as can be expected, because no good deed goes unpunished on the internet, they put this bot out there. A bunch of people, I think from 4chan and other places, got hold of it, started spewing all kinds of garbage and language and bad language and obscene statements at it. Within 3 days, that chatbot had become a racist, a vulgar, just things spewing out all kinds of trash at everyone who wants to speak to it. It's real data. That was not the issue here. The problem was it was being deliberately sent certain kinds of data just for the heck of it, just to see what would happen. Okay, so we were asking for examples, right? So think of this as an example, right? So you have a bot and you want to train it to converse with people. In all your research papers, you assume this. No one ever worries about this. But the cases that we worry about is this. What happens when you have data that you apparently have collected from some source and might believe to be ground truth, but is in fact biased under this definition of bias? What are your choices? You really have two choices here. You can say, I don't care. Let's just move on. Essentially, pretend you're here. Other option is, no, I do care. I don't trust my data that much, so let me modify it. Kind of move towards here. These are your choices, and I'm not saying that one choice is better than the other. I'm saying if you actually want to do something about bias, you don't have too many options available to you. In this setting. There are other settings, but in this setting, this is what you need to do. So this whole idea of modifying the input, it's, I think, helpful. And I only just came up with this picture after talking to you, so this is kind of a new thing for me too. It's helpful to think about this, right? That we might think we're here, but we're actually here. And now we have to decide which of these two worlds we want to be in. And that decision is up to you as a data scientist, right? It's not up to me. I would argue, of course, that we should care about bias. But again, it depends on your data, right? If you have reason to believe that you don't want to tamper with your data, then don't. Then it is what it is. Okay? So I don't know if this helps clarify some of the discussion we've been having about whether it's okay to change the data or not. But that's essentially what's happening here. We're making choices about what we think is important versus not. And of course, the hope is that when you do this, you don't go from ground truth to crap. You go from ground truth to something slightly modified, but it's still decent. Okay? That make sense? Okay. So let's get back to this. So I asked you all to think about this while you were drinking your tea and coffee and stuff. What do you think? What should we do? How do we change these labels to fix this problem? It's actually the solution I want to describe is going to be like, oh, that's like, obviously simple and dumb. So maybe you're thinking too much. What's the obvious thing you could do here to get this to work? Yeah? Why do you think that might help you?
Because if we are having more number of tuples with a particular class, so it may affect the system.
So in other words, if you have too much of this and too little of that, that's going to skew your number. So try to balance out these numbers by sampling. Okay, let's write this down. Sampling. Good. What else?
So this is something which is already taken care of in design experiments.
Pardon me?
When we design an experiment, we say that the sample should represent the population.
Yeah.
So probably are we redoing or reinventing whatever was already there?
You are right that in a controlled experiment, you have a much more degree of control and you can examine the attributes of your patients, let's say in your study, so you can make sure you have balancing across all the characteristics you care about. We're in an observational setting here where we don't have a controlled experiment. Most settings where we do machine learning, we don't have control.
Reinventing what is already there in the experiment.
Um,
Whenever we design experiments, that should be that way. That was already there, the different sampling techniques and stratified sampling.
In a sense, yes, because sampling is a tool that is universal. No one owns sampling, so yes, I mean sampling is a much more general tool than is just narrowly specific to this problem. But sampling is not the only thing you could do here. There are other things you could do.
Just restricting myself to sampling.
Yeah. So sampling is an obvious strategy to balance things out, right? So if it means that we recreate,
We have forgotten that perhaps we are not doing it, so you must do it. That's what we are saying.
essentially, yeah, because the data was not under our control to begin with, right? So make our data look more like what it would be for a designed experiment. What else could we do?
We can arrange them in a random fashion.
Explain.
Like here we are having all 1, then all 2. So we can have 1, 2.
So you scramble these labels up, randomly permute them in some way. Okay, so randomly permute labels.
And why are we doing
To make sure.
what is the rationale behind randomly using?
Don't ask me, it was his idea. Ask him. I don't know, I'm just writing stuff on the board. You ask him. Defend your rationale to him.
Because weights are updating, and like we know that if we can resolve errors at the early stage, it will always be good. So we are giving the system the another type of threat for which there is a different output. So if it is producing like large errors, so it can correct itself. At the end.
I'm not able to appreciate.
He's not able to appreciate this.
So you are there.
No, but I would much rather just, I want to be agnostic on this point, right? I mean, I think it's a good discussion, but can you maybe state your objection again?
I was just saying, why we should do permute something in a random fashion?
What's wrong with that?
What's right? That's the question, right?
Okay, fair enough. I mean, I guess the benefit, the burden of proof is on the modifier, not on the thing. Okay, so I think the rationale for random permutation was to, it's almost like a sensitivity analysis you're trying to suggest here, right? That if you randomly permuted and things were good, then what? Maybe I don't like your method either now anymore.
This is something which we have practically tried.
What he is trying to say is that I'm grabbing.
No, he's actually tried this. Okay, so tell me, you tried this. So what is your rationale for trying this? Then?
When we train our system using a random organized data set,
Yeah.
so in that case, if we are testing with the unknown data set, it produces better results as compared to if you are training the data set with that standard method.
But you don't change the labels.
We are not changing the labels.
But here you said you're going to change the labels though.
We are not changing the labels.
But did you just say to randomly permute the labels? No.
No, label is fixed.
Oh,
Only arrangement.
but how would that make a difference?
It actually sometimes.
Hey, if you have a garbage input and then you have a garbage input, nobody's happy, but then nobody's happy also.
Yeah, so we don't.
If everyone's wrong, we're all right. Where's the that was the from yesterday? Okay, so maybe I misunderstood what you were saying here because I was thinking of something slightly different to this. So I'm gonna rub this out because the other thing that you could do is, okay, so let me back up a second here, right? Because essentially I'm trying to get you to reverse engineer this paper, which is always a fun thing to do with the paper, right? So reverse engineer what they did. think of this, think of the classifier boundary. Let me see, do I have blue? Yes, I have blue. Okay. So let's say we have, blue points and black points. So this is I'm building some kind of classifier. Let's say it's a linear classifier. I don't know. Okay. And I have some linear classifier that goes along with this, right? And I have some bias in my system, so I would like to change my labels somehow to improve the bias. What I might like to do is, if things are already close to the boundary, okay, maybe I was slightly wrong with the decision on one of these things. So what I would like to do is say, okay, for things that are close to the decision boundary, those labels I might flip. So I might replace this by that. I might replace this by that in order to balance things out. But I won't take something from here and make that into a circle, or take something from here and make that into a cross, because that seems like a bit too much, right? So in other words, the intuition behind some of these modification strategies is to say, look, if I'm already feeling a little uncertain about my data, and I'm willing to make some changes, then I should make changes that are kind of as unintrusive as possible, which would be changes where they were so close to the decision boundary anyway that there could be natural ambiguity about where things are. Okay? So in fact, this first paper that I've been talking about this time, their idea is basically this. Take your data set that appears to violate some notion of statistical discrepancy, okay? Look at the labels and find a heuristic to modify labels based on how close they are to the classifier. Of course, this is a chicken and egg problem because I don't have the classifier, right? So there are some heuristics they use to say, look, we'll build some kind of approximate ranking scheme to figure out how close things might be to a boundary. Use that to decide which ones are really close and flip only those.
You mean to say if you have good men and bad men, then all the moderate criminals serve as good men?
Or bad men. Yeah. So people on the boundary, if you're on the line, going from here to here is not so bad. But if I'm all the way over here, shifting my label to all the way over there might be considered a bad idea, right? So that's the rationale here. So it's the idea of you want minimal change. And I'm going to emphasize this point because this is going to come up later as well, that the trade-off here, that the trade-off that you're feeling between fairness and accuracy is in some sense a way of saying, I want to minimally modify my data, minimally being the important phrase here, to achieve what I want without tampering on the data too much. Because if I don't limit myself, I can do all kinds of crazy stuff to my data, right? I can just blank out everything, do anything, whatever. But I want to do this in a very sensitive, deliberate, kind of delicate kind of way. And that's what they do. So they have a couple of strategies. One strategy involves
Why don't we do away with these moderate principles?
just get rid of them.
Don't use that.
We only want the extremists. We don't. So this would be a.
Instead of flipping, which is a deliberate tampering, we do away with it.
Just get rid of them, delete them. So I was talking actually in the break about this. It's saying that one strategy could be reasonably to say remove these elements. Another strategy for achieving the system, and that'd be perfectly fine. Yeah. For some reason in this paper they didn't do that. I don't know why. That's a perfectly natural thing to do. It eliminates the moral objection of changing a label by saying just remove them.
Remove that particular attribute also.
Well, you can't remove an attribute, right? Because the only attributes here are the Y and the G, and you can't remove them. So, yeah. But that won't change anything, right? No. If you're trying to enforce this, the only attributes that matter are this or this. Nothing else matters. Doesn't matter. That won't affect this. It's a projection, right? So, yeah. So, yes. It will, won't it? Well, if you delete or if you flip? It might, but not much. Right? This picture really, in your mind you should think of as looking like this, right? There's some kind of big gap here, right? Most of the points are well separated, and you have the boundary here, and you have a few points that were, remember, these are a few points here, and there was a few points here. You're right that you'll change the decision boundary a little bit if you change it, but the hope is that if you choose points that are close already and change them, you won't change it too much. Whereas again, if you change one of these points, then you really would change the decision boundary a lot. Right? So this is somewhat of a heuristic. It's a little ad hoc. I don't have I have an intuitive sense that I want to keep my decision boundary more or less the same, but I don't have any precise way of guaranteeing that. This is really a heuristic way of trying to say that, oh, it won't happen. So when I tell you, oh, it won't change too much, you don't have to believe me because I have no proof of this. I'm just saying, well, it seems like it should be okay, and that's really a heuristic. So I agree. It's a rough idea. But that's basically what they do. So they have various heuristics. One heuristic is to do sampling to normalize the size of the population, so you get that. There's another reweighting metric where you reweight different tuples so that if you have, you give more weight to things that balance this out properly. And then you do this kind of modification of relabeling of data. Near the boundary.
Slightly different way to read this thing will be make sure we are as close to the ground truth in the data as possible.
What's ground truth?
So make minimum changes.
Yeah, so that's something. You can relabel these in a minimal way.
Yeah.
So the way they propose to do this is to say, look, for every point, we will figure out some proxy for how far it is from the boundary. We'll sort the points by distance from the boundary, and we'll work our way up from the boundary. Minimally changing so that we can, greedily changing things so that we can get the desired balance that we want.
It still depends on the model size, right?
Yeah, sure. Absolutely.
But we want the input part to be independent of the model.
Yes, but like I said, if you're, these techniques tend to be linked to what kind of model you're building.
Yeah.
If I'm building a regression model, this may not work anymore.
No, like even in binary classifier, we are assuming we are using a linear.
No, the decision boundary is well defined regardless of whether I have a linear separator or something else, right? Distance from the, so suppose you have an SVM, we saw this SVM yesterday, right? And your SVM boundary looks like this. There's still a sense of distance from the decision boundary.
That's true, but we need to have the SVM boundaries before we can calculate how far.
So one of the things they do is come up with some heuristics, which are, heuristics, for trying to estimate what their decision from the decision boundary might be before doing the actual classification.
Ideally, you would not want to calculate the decision boundary and pick.
Ideally, we'd have good data. What I'm saying is, these are things you could try to do. I'm not saying these are all the best things to do. I'm not saying that they should always work, but these are some things you could try. These are some ideas you could actually implement to get these things to work. And maybe in some cases, the experiments basically suggest that, some of these things work well, and in certain cases, some of them. So it's kind of inconclusive, which is why, I think this was an interesting piece of work to sort of discuss how to do this. I'm not necessarily convinced this is the best way to go about this problem. I think there's more work to be done here to try and think of this better. And in fact, I'm going to describe another paper that sort of comes at this from another angle altogether. Okay. So again, backing up, we want mechanisms. We want to modify. There were 3 different ways we could build a mechanism to be fair as well as accurate. We're looking now at the case of modifying the input. And in that, there were 2 categories: modify the labels or modify the data itself. And we've just talked about how you might modify the labels in order to achieve balance with respect to this notion of bias. Okay? Yes?
The data which is wrong belongs to that second category, 1, 2, case 2. So we are trying to modify that. That means we are trying to either put it in case 1 or case 4.
No, we're starting off with data that we believe is correct, but has bias in it. We would like it to be here, but we're not that lucky. So we're trying to modify it so we get to here. Right? That's a little bit false, but it at least has no bias in it, right? Because the goal is to remove bias in the data. See, that's the dilemma. If you believe you're here, then you don't want to move. But if you're actually here, then you say, okay, maybe I'm willing to move a little bit, depending on how important you think these things are. Okay. All right. So the second part of this discussion of modifying the input. Right? So this, again, this is not an unusual technique. So it's a technique that appears in many places. So we had a paper on this a couple of years ago where we looked at not this measure, but the related measure of disparate impact, which was if you recall, the ratio of these two things. And again, the goal was to modify the data so that when you now train the classifier through it, you would make sure that you would not have disparate impact in the result. So the way we chose to approach this problem was slightly different. And our framework was the following. So what we said was that, so you have some black box, some model that's being trained, and you have the training data coming into it. And because we don't have access to the model, so in some kind of black box world, just like here, either you can't see or you don't want to touch the classifier, but you want to make sure that what you're learning is not going to absorb bias in the training data. Okay? And so the question was, how can you modify this to make sure that happens? Just the same way as before. But the approach that we thought we'd take is to sort of think about it just in a bit more systematic way, to say, if you are measuring the results of the algorithm for disparate impact, what can we say about the training data that would tell you something about the likelihood of disparate impact no matter what the black box looked like? So for example, could we say something like, so given D, given the data set D, there exists some modification procedure with, let's say, a knob controlled by a number delta, some parameter delta, such that any model trained on so this gives you some D prime, does not have disparate impact with parameter some f of delta. So what am I saying here? What I'd like to do is the following. I'd like to not care about what the procedure is, right? What I'd like to say is that I can do something to the data so that no matter what happens inside, the result just cannot be biased. There is not enough information in the system anymore for the algorithm to learn a biased outcome. This is the goal. Okay. There's this whole idea of, okay, we'll change the training data to be unbiased in the hope that now the classifier will not give you biased outcomes, right? So we're using this measurement, but really this is going to be the output of the classifier, right? You can measure this on the training data with the actual labels, or you can measure this on the classifier output. What we want is that the classifier output does not have bias. So we want to do something to the inputs to make sure the output does not have bias. In the previous procedure, we kind of hoped that by making the original data unbiased in this particular way, then the classifier would work fine. But we didn't have any formal guarantee this would happen. What I'm saying is, can we actually give a formal guarantee? Can we say that there exists a way to modify the data such that no matter what this box is, any binary classification box, whatever it is, decision tree, naive Bayes method, or whatever, or SVM, or neural net, whatever you do put inside here, it will not have disparate impact. Okay? If you can then show such a procedure exists, then you're in business now. Because now I can do this and essentially guarantee I'll be okay in a formal way. So that's the goal. Okay? And so it turned out that what we were able to show was the following. Something that's reasonably intuitive, but so again, think of our attributes. So we have the input, This is X, and this is Y, and there is some attribute G, which is the protected attribute that you worry about, and the discriminatory attribute. And let's assume that the algorithm does not want to be biased, so it actually does not even look at G. So this is even covering up G, right? It might even be doing that. And so our goal is to say, basically, is there some kind of information flow from G to the rest of the data that the algorithm might be able to capitalize on to get a biased outcome? And is there a way to cut this off, cut off this information flow? Formally, here's what you want to say. Here's what you are able to say. That suppose there exists a procedure, sort of a learning procedure that predicts G from X minus G with error epsilon. Then there exists a machine that can predict Y with disparate impact the actual function G doesn't really matter here. So what is this saying? What this saying is trying to capture an intuitive idea, but formally. How do we know if information about the protected attribute is getting through to the system and possibly exploited? Remember, we're talking about a worst case scenario here. So I'm not talking about actual exploitation, I'm talking about possible exploitation. Okay? So how do we know if enough information is getting through the system that this can use it? In other words, how do we know that the system, even though we've removed the attribute of problem, is not somehow recreating it and using it to be discriminatory? So for example, if you're doing hiring and you're looking at CVs and you don't want to be gender biased, one obvious thing to do is to remove, don't ask for gender. But it's very easy to look at least in certain countries, you can look at the name of a person and with a very high level of accuracy, figure out what their gender is going to be. Right? Now, of course, a model trained on American names will not work in India and vice versa, but there are some countries where it's very easy to do this. And in the US, it's very easy to do it. I suspect, I don't know if people have done it, but it would be pretty easy to do this on Indian first names, to figure out if a name is male or female. I mean, I don't know if any of you have tried doing this, but it seems like it would be easy to do. Chinese names are a bit harder though, because you could have males and females with many of the same names. So you could reconstruct the attribute that has been removed and use that to be discriminatory. So you have to somehow figure out if there's enough information flowing from this attribute to other attributes around that the algorithm can take advantage of M. And what this says is that you can quantify this relationship. You can say precisely that if there is a learner that can predict G from the rest of the attributes with epsilon, read this as saying there is information flowing from G to X minus G, right? So if there is information with this degree epsilon, then you can discriminate up to a certain level. Obviously, the larger this value is, right? If the only error you can get is very large, then you're not going to get much disparate impact and vice versa. So actually, it's an inverse relationship. So this is an important result, right? Because what it's saying is that I can quantify the amount of information flowing through a system, leaking from my G into the rest of my data by building a learner. So it's kind of like an arms race problem, right? To beat a learner, you got to build a learner. It's similar to that, right? I mean, it's a similar flavor to this. It's not a cryptographic game, of course, but it's a computational game. Where what I'm saying is that I replace an idea from information, I replace talking about mutual information and information flow by talking about a computational device that does the same thing for me, that there is an effective procedure to do this. Because what this also means is that if I now want to make sure that I can modify my data so as a learner cannot have discriminatory output, I just need to fix this. I need to make sure that no such learner can exist. Because if I can guarantee this, and I should have said, so as long as I can guarantee this doesn't exist, that such a learner cannot be produced from the data, that any learner on this data is going to get very confused, going to have high error, then I'll be safe here. So my strategy for data modification is not, a specific set of attacks in the data that look reasonable, but is based on sort of this argument from here, this more formal argument from here. So the strategy is take your data and do something to it to destroy the connection between G and the rest. If that can be done, then you have your answer. And then the question is how to do this in a minimal way.
Yeah, but there's one observation. If you're not considering Y here,
Yes, I'm not.
then it's very possible that doing something with this X minus G might also affect Y anyway.
It will. And in fact, we show that. You can actually, so you can run your classifier on the original data, you can run classifiers on the modified data, and you can look at the difference in accuracy you get. And you can actually, well, it depends on the data actually, as it turns out. There's some data sets which are well known for being problematic, that are very hard to balance these two terms out. And there's some data sets where actually you can get pretty much the same accuracy level without any change while being much more fair.
So what do you do with those that get affected?
This is a choice, right? Again, this goes back to this problem. So what you're saying is that in those cases, you're having this much larger tension between the data and the natural signal defining effectiveness of the procedure appears to be coming from the attributes you don't want it to be on. So there's some intrinsic bias in the data. Now you have to decide what you want to do with it. There's no clear answer to this, right? And you could say, that is what it is, I'll live with that. Or you could say, look, I'm not allowed to do this. I need a different data set.
Actually, you're not solving the problem in general. You are just changing the problem definition. What you are saying is, rather than you're decreasing the accuracy, and it's quite possible that the system may not achieve what it's being used to achieve. For example, I want to find out those criminals who are about to do something.
Right.
And this does not allow me to do that by decreasing the accuracy.
Yes.
And I'm not happy.
You may not.
Ultimately, the user, the police, for example, doesn't know that.
Right.
He's the user. He doesn't know that field to be there.
And again, ultimately, and this goes back to this point we've made before, I think, right? So there are two ways to deal with this problem, two ways to think about this. One aspect of this is that your measurement of accuracy is with respect to the data you're currently using. If there is bias in your data to begin with, which is the reason we're doing this in the first place, then all you're saying is that I'm unable to recreate the results from a bias set. This is not necessarily a bad thing. That's one aspect of it. The other aspect of this is that if you are fundamentally forced to choose between a fair outcome or unbiased outcome in this sense of unbiased and an accurate outcome, you could either say, okay, I have to choose one or the other and I'll make my choice. Or you can say, is it maybe something to do with this data set that's forcing me into this choice? That a different data set might have allowed me to not have to make this choice. And I think I would argue that this would be a sign that maybe you should be looking for a better data set to be working with. Maybe. So these are the ways I would interpret the consequences of seeing this strong trade-off between unbiasedness and accuracy. I'm not saying there's a clear answer here.
So in this alternatively, you wanted to reduce the dependency in the data set.
In the data set, or you want to reduce the information flow or create independence between the attribute of concern and the rest of the data.
Attribute of concern in G.
Yeah.
Why is it
The gender attribute or the race attribute or whatever it is.
Every attribute is important?
No, but the only certain attributes are problematic from a bias point of view, right? these are told to you, right? I mean, in India, in the constitution, they've listed specific set of things that you are not allowed to discriminate against. No, it's perfectly fine to discriminate against whether you have a mustache or a beard or not. There's no problem with that. But there's
What he's saying is that you cannot ensure anonymity by hiding.
Right.
You cannot be anonymous just by hiding it behind the race. But there are other attributes which we treat. So if I hide my name,
Yeah.
but then
Yes. Yes.
you are arguing, then obviously you say,
Yeah. Right. Okay. So how do we do this? How do we then? So if we, given that we have this lemma as a thing, I mean, it actually is a formal statement. We use lemma as a way to work with the data. Can we use this as a foundation for a procedure that will allow us to minimally change our data to ensure that this can't happen? In fact, one of the procedures I will describe will make this error half. That you'll be completely indistinguishable. There'll be no way you can tell G from the rest of it. And I think one way to think about this, to build some intuition for how this procedure is going to work, is again to take a very simple example. So I'm going to draw another example here, just to see.
Can you clarify? Because there was a famous track on K anonymity.
Yeah.
Not similar to the K anonymity, and there was
I do remember. So I mean, so what kind of attack are you talking about?
saying that the whole definition seems to be quite close to that.
So this is not entirely unsurprising.
You say that you remove sensitive attributes, yet people are able to point out to the person who attribute.
Yes. So the original K anonymity paper was an attempt to create ambiguity by saying that there are always K answers to the question, no matter what you do. In some sense, they were trying to create a level of entropy. Then, of course, L diversity, which is the next paper that came along, said, okay, let's formalize this idea of increasing entropy. And then, of course, this T closeness, which I had sort of worked on, which is the paper that I wrote on this topic. Well, I was on it. So it's funny you mentioned that, because I didn't, but we will use the Earth mover distance here just the way we used it there. So there is a connection, but it's in my subconscious. I didn't actually realize there was a connection there. There's a funny story about T closeness that I'm happy to share once the cameras are off. So. Okay, let's think of an example here. And for that case, I'll need, again, two colors to be easier down. So let's say we're looking at, what's the best number for this? Let's look at, class 12 scores or SAT scores or some kind of score that you get from high school, right? And let's say we're looking at gender bias here, just for argument's sake. And let's say we collect a data set and we start plotting. So we have the distribution of scores, and we plot two curves, one for each gender. So let's say one curve looks like this, and another curve looks like this. And I'm not going to say which gender is which. You can choose whichever way you want to do it. I don't really care. It doesn't matter. So intuitively, these are the two curves for the two different genders. Suppose I was given a score. With what accuracy could I tell what gender the person was? Now in this case, it's reasonable to expect that if the score came from somewhere here or came from somewhere here, you'd have a pretty good chance of estimating what the gender was. And if the score was somewhere in the middle, you would not. Right? Okay. Let's pull them apart. So let's say my curves in fact look like this. Okay. Now, if I asked you, okay, here's a score, I give you a score, tell me what the gender of the person was, you'll have a much better chance of guessing it because they're so far apart. Right? There's only a small region in the middle here where you might make an error. In other words, the amount of error you have in the process relates to the degree of overlap of the distributions. Right? Okay. Now think of this process. So think of this being the simplest case. If you have a data set that looks like this, there is going to be some error with which you predict the gender from the score. If the data set looks like this, there'll be a different error of predicting the gender from the score. And if the data set looked like this, you'd have almost no hope of telling them apart because the overlap is so high. So if you to think about the process of how we might modify a data set in order to make this hard to do, which will then by this result make this hard to do, which will mean that we are happy with our classifier. We somehow have to make this hard, but to make this hard, if you go from this example, you essentially want to take these distributions and move them together. Right? The closer you can blend these distributions, the more confusion there will be for any classifier. And notice that this is agnostic to whatever classification technique you use. I'm just saying the distributions look very similar. Information theoretically, there is not enough information in there for a classifier to work. I don't care what you're doing, no matter how smart you are. Right? And those of you who have ever taken a class in information theory, this should remind you of a result called Fano's inequality that essentially relates the amount of mutual information in a system to the effectiveness of the best classifier for reconstructing the input from the output. Okay? But that's the idea here, that because I want to make my statements independent of whatever system I'm using to do the classification later on, I have to make statements of this kind. And if I can do this, then I don't care what you use. You will not be able to tell them apart. I can make this formal. So the question then becomes, what does this mean in general? To sort of put things together. So formally what this means, I should, let me plug in my, what I formally want to do is something like this. So let me say, okay, so this is the basic idea. So what I want to do is say that I want to look at the density function of the data. So some point x. Let's say I have two classes for now, but in general I could have more. Okay. Thank you. On me? Yeah. I want to make these two distributions look the same. And these are, of course, multi-dimensional distributions, right? So I want to make them look as close as possible. In particular, if I define some appropriate distance function, I want the distance between these two density functions to look very little. And it turns out there's a very nice way to do this. If you have, well, if your distributions lie in one dimension, there's a very clean way to talk about this. That basically, if you have these two distributions, and you have one here and you have one here, well, I should have put them here, and you want to move them to each other, then what you can do is you can define this thing called the earth mover distance. So the earth mover distance, how many of you have heard of the earth mover distance or anything transportation distance or between distributions? Okay, so let me define the notion. So think of, so the earth mover distance is called that because it's about, well, moving earth. So imagine I have two distributions and they're kind of bumpy things on the plane, right? And imagine those distributions are actually piles of earth, piles of mud. There's one pile of mud there, there's another sort of big pile of mud here. And I have these little ants, right? They're picking up little crumbs of mud, they're walking over and they dump. And they pick another piece and they walk it over and they dump. The goal is to make one profile look like the other profile. So whatever there's extra stuff here, they carry it over there. Where there's a deficit, they carry it from back there. And they're walking and they're ants and they get tired. They need energy. So you supply them with sugar to keep them going. How much sugar do you need? That amount of sugar you need is the distance between these two distributions. So more formally, the earth mover distance, so if I have two distributions, so if I have a metric, so I have some kind of metric space. So let's say for now, let's keep it even simpler. Let's say I have the line. I have points on the line. And I want to compute the distance between these two distributions. So what I say is that, so I have one probability distribution, let's call it P of x, and I have one probability distribution, call it Q of x, right? So the earth mover distance between P and Q, right, is the min of the, basically the integral of okay. So what this is saying is the earth mover distance is this minimization over this weird pi function. What it's saying is that this pi function you can think of as a joint distribution between the two distributions whose marginals look like each of them. Right? So if you think of this joint distribution, on one side its marginals look like P of x, on the other side its marginals look like Q. But this is this has fractional values in there. And what this is saying is, okay, I transport this much mass from here to here, from point x to point y. So if you think of a point x here and a point y there, I move some amount of mass from here to here. I might move some amount of mass from here to here. I might move some amount of mass here to here. The goal in all this motion is to make sure that this is what happens. Okay? So it's a minimization over all possible transportation plans of the amount of energy required to do this. That's why it's called the earth mover distance. It's got many names. It's called the Mallows distance, the Wasserstein distance, the Kantorovich distance, I could go on for a while. There's a whole bunch of them. It's been reinvented over the centuries. The most recent incarnation is the earth mover distance. And so it turns out that that if you now say, I have a collection, so this could, for example, this could be now, you could have multiple values. We're not even limited to the case when you have just two things. You can say, I want to find now, so find a distribution, a new distribution R, such that R minimizes the sum of the distances of all the conditional distributions. So we'll call them Pi. So we'll call this distribution P0 and we'll call this P1 for these two values. So for all the Pi to R, okay? And if you find this R, this will be a good minimizer. It will be a good minimizer. It'll have a minimal amount of change. So this is the amount of change you're going to make in the distribution to modify it. And so you'll have the smallest amount of change possible. So in other words, the strategy to merge these conditional probable distributions together in order to make it impossible to distinguish g equal to 0 from g equal to 1 involves saying, take my conditional distributions, find the point that minimizes this quantity, and then move them all the distribution to that. And now you can say, well, how do I do that? And this is the beautiful part, that if you use the earth mover distance, it turns out that all you have to do is compute, and this is, again works in one dimension, you compute the cumulative distributions and take the median on each coordinate. And that distribution, which has that cumulative distribution, is in fact the answer. And again, there's the paper that I linked to has more details about this. Okay? So to sort of put it all in perspective, what I'm saying is that you can take your data and formulate an optimization strategy that will give you an answer that will guarantee that you cannot distinguish the classes from each other, thus guaranteeing you don't have disparate impact, but it also has amount of repair, amount of change in the data that in some sense is small. You're trying to minimize some cost of transportation. Right? And so in that sense, you're trying to balance out the amount of change you make in the data and the amount of bias you eliminate in the process. Okay? So this is still, this paper is still a work in progress in the sense that there are still limitations to what we can do. While the theory of this works fine, in practice to implement this beyond one dimension is a little bit harder. So we have a strategy where we do it in dimension by dimension, but repairing the data dimension by dimension does not fully guarantee that you've removed all the signal in the data. So the actual algorithm we have is still a heuristic for this. It's only guaranteed to work correctly in one dimension. In fact, there's been some recent follow-up work where they look at how to do this manipulation in high dimensions using some kind of Bayesian model, some likelihood model for how to integrate the distributions together. So there's ongoing work on this topic, is basically what I'm trying to say.
And when the whole number of dimensions increase,
Yeah.
then the distance also becomes doesn't give you anything because the central limit theorem.
Yeah, so I mean, that's always the case, right? When you get to high dimensions, no distance is sort of meaningful at that point. Yes, that's always the problem. I mean, at that point, I'm not quite sure what you would.
Usually, in practice, we don't.
It's not, yeah, it's not that much of a problem. Right, for these kinds of things, you don't usually have such a problem. Because well, the number of dimensions still is unfortunately the number of features in your data. So if you have a lot of features, then you will have a lot of dimensions.
Suppose what happens now that you do some dimensionality reduction before training.
Yes.
Then do you apply this? If you apply it becomes meaningless because after the dimensionality reduction, the number of dimensions are not very useful or intuitive from the human point.
But the goal here is not what a human thinks, right? The problem here is to remove signal that an algorithm can learn. Just because you've done dimensionality reduction doesn't mean a clever algorithm couldn't reconstruct what you're doing.
So, but we have done dimensionality reduction, perhaps that problem can solve because then G becomes G. That is something which is familiar to all others, and something by two-dimensionality reduction you can solve that.
So in other words, what you're saying is that if the problem here is that G has got correlations with the other features, and if you did the correct kind of PCA or something, you've essentially isolated the effect of G, and then you could strip it out and you'd be fine. That may be, yeah. But then again, you have to hope that it'll work. The problem is, can you give a guarantee on that? At least here you can give a formal guarantee. If you do this, then you will eliminate everything. With your method, it might work, but you would have to somehow argue that it in fact was guaranteed to eliminate this problem. But I agree, it's an interesting idea. So just do PCA to decorrelate the data, and then strip it off, if that's possible. The problem is if you have nonlinear correlations, then you'll need something beyond PCA. PCA won't go.
For the dimensionality reduction, we go for orthogonality, and
Yeah.
that produces, removes the correlation.
Yes, but only linear correlations. I mean, it only removes linear effects. It doesn't remove nonlinear effects. Right? If your data lies on a manifold, PCA is going to not do anything good useful for you.
So what non-linear PCA is not non-linear design can be.
Oh, you said to do a nonlinear. So which one would you use? So you can use, you can build an autoencoder, or you could do manifold learning. There are things you could try. Yeah, they definitely are possible.
But then that doesn't become intuitive because ultimately the human being doesn't know which, for example, in a social setting, which social attribute is.
Sure, but I also want to harp on one point. I think it's important to be able to make formal arguments about this. And I think, while I think trying all these methods is perfectly reasonable, it's a good idea, but I think it's important to be able to say what in the worst case, what's going to happen. Just from a theoretical point of view, the reason why I think we tried to do this was to say something, what can you say formally? Oh, Pi is the conditional distribution conditioned on the group value being I. So you could have multiple values of the group, right? So if the group is, say, race, you could have like 4 or 5 or 6 values. Then you have so what you're doing is you're taking, okay, look at the conditional distribution data for this value of the group, for this value of the group, for that value of the group. They intuitively need to be put together, because if they're far apart, I can tell them apart, right? And so putting them together. And again, just to reiterate, this idea that that the separation of the conditional distributions is what allows you to tell them apart is the core idea of Fano's inequality. So.
Same idea as dimensionality.
no. I mean, okay, so the idea of dimensionality reduction in the ideal world is to find decorrelated directions that capture the variance in your data, right? The PCM, direction of maximum variance, and then subtract them off. Okay. What does that have to do with independence assumptions here?
When you were saying defining the distance,
Yeah.
but I do not know. Let me think. I'll come.
Okay, sure. Yeah. Yeah. It may be, yeah.
Suppose we have attributes where there is a dependency, because in the dimensionality reduction we can reduce the dependency.
If it's a certain kind of dependency.
If it is certain kind of.
Yes. If it's a linear relationship.
So actually we are reducing the bias time, because giving more attributes of a similar type, which are having some relationship, will be a bias to the system,
Why?
because you are giving similar kind of input, similar kind of attribute again and again, means you are using multiple columns, suppose. You are using length, you are using width, you are using.
But see, but you don't know what the classifier is doing, right? I mean, it may be that the classifier realizes that all these are saying the same thing and decides to only use essentially one of them.
If classifier finds out that they are same,
Right.
then there is no problem.
The thing, we don't know what the classifier is doing. It could be doing anything. We make no assumption about what the classifier could or could not do. Right? Yeah.
When we do any transformation on the data, we have to preserve certain things.
Yeah.
Because, like, the point is to do something with the data, just not remove bias.
Right.
Yeah. So, how do we know that, like, other properties of the data are preserved?
We don't. Nothing I said will promise you anything but any other properties of the data.
Okay.
All it's promising is that you will be indistinguishable, and in some sense, we are not making too much change to the data. That's all I'm promising.
Is it possible that this technique will, like, take out all the power of the data?
Yes, it's entirely possible. Yeah. And in fact, like I said, in our paper, we have experiments where, if you think, okay, so now you can do things like this. You can say, I didn't say this, but you can make this, you can also put a knob here. You can say, okay, how much do I want to move these things together? So intuitively, I said I want to take my distribution and move them together. I could also move them a little bit. Right? So I decrease the power of distinguishing a little bit. I can go all the way. It's a smooth motion there. So I have a knob. So my knob can be turned all the way to like fair heaven all together, or it can be turned a little bit, so I move that. And I can make a plot. I can say based on the knob, based on how I modify my data set, how does my accuracy look? So you can make a plot that looks like this, right? So you put a plot here, you can say accuracy, and you can say the degree of fairness, right? And you can see what these plots look like. What you want is a plot that looks like this. What you don't want is a plot that looks like this, right? What we see typically, I'll caveat this by saying we didn't try a huge number of data sets, but the ones we did try and the ones we've seen other people try in other contexts seem to vary between this and this. So you get accuracy degradation, no surprise there, but you don't get a huge amount of degradation. And you rarely see things like this. But again, that's not to say that I can't construct a data set with exactly this will happen. It could easily happen, right? If in fact you're precisely deciding based on the group attribute. If I destroy that, then you're going to have zero accuracy at all.
Can we say that in this method, without transforming, we are doing this?
We are transforming though, because I'm changing the data. I'm going to modify the data by finding a target distribution and moving all my data so it looks like the target distribution. So I am modifying the data.
How do you precisely do that?
So, okay, so in the case of the Earth, so here's what you do. So this is where it gets a little bit. So imagine now that my data sets they're all one-dimensional, okay, for now. And compute the CDF for each distribution. So now I have a CDF for this. Once you have the CDF, you can look at the inverse CDF. So in other words, so if this is a CDF for each value, so you can look at a particular value lambda, and you can say, okay, for this percentile, what value on the x-axis corresponds to that percentile, right? So this is I'll write this as the inverse cumulative distribution, right? Because the cumulative distribution, so the distribution is F, the cumulative distribution is capital F, and this is F inverse. So it turns out that the optimizing R for the Earth mover distance has the property. That's all okay. So let's say this is my distribution P0, and I had F inverse P1 and so on. Then the property we can state for R, we can prove this, is that the inverse cumulative distribution for the target distribution R, the optimal solution, is equal to the median of all the inverse cumulative distributions. So it's a kind of an indirect definition of the optimal solution in terms of its inverse cumulative distribution. But this is enough to construct R explicitly. Because you can construct these explicitly from the data, then you can essentially figure out what these medians need to be, and then you can do the inverse on R and get the distribution on R. And that's how you do it. So this is kind of a nice property, that by choosing this particular distance function, you get this nice characterization of what the solution is. Otherwise, you're right, how do I compute this? So that in this case, we kind of got lucky there. Pardon me?
Are we solving any problem on this system? Some numerical?
I'm not following.
Some numerical we have to solve on this?
Well, you have to compute the median.
Like you're saying in the lab you'll be doing something?
I have actually, so I actually have the code, all the code we used to do this, and I want to construct that into a lab that we can play with, because it'll be kind of fun to play with this and see what happens with it. Yeah. Okay. So let's back up again. We've been talking about how to modify the input to look at, to make an input such that an oblivious classifier would automatically not be biased. So we won't have to worry about the classifier. We can use whatever we want, right? All our focus is on the data. And the ideas that came through here in all of these, in the different forms, was that you want to minimally modify the data, so do as little damage to it as possible. So there's some kind of balance between how much damage you do and how much fairness you achieve. But you want to somehow do things in a way that you've destroyed the signal going from the protected attribute to the rest of the data. And that's the goal you want to achieve. And if you can somehow do that, then you get what you want. And so we talked of a heuristic approach based on modifying the labels, and a somewhat more rigorous approach based on thinking through this information theoretically. So what I didn't mention here, the underlying all of this is certain information theoretic intuition about how this works. But it doesn't actually show up in the analysis, so I didn't bother to mention it. But if you know information theory, like I said, you'll recognize some terms here that I'm using here. So that's it. And so I guess the next phase would be to then talk about part 2. Can you build a classifier explicitly that would take into account the fairness criterion that you have? So in this case, you are opening up the black box. It's more like a white box. You're the person inside the company building the tool, and you want to build a good tool. So notice that I didn't talk about things like, okay, how do you modify the input to do individual fairness or things like that. These are questions that I think that actually have not been looked at in full form yet. So there may be interesting things to think about here, to look at. Okay, so I know it's like 12:55. Do you think it's a good time to stop here? Maybe 5? Huh? Well, we have to talk about this, right? Because I was gonna not. So I was thought I wish I could just give the afternoon off maybe today.
Okay, that will be great. But
And then that'll give me some time to prepare some things as well.
But many of the people are local, they are from like
Yeah.
So if you can give some exercise that they can try out their own, that will be fine. So that they come prepared for the lab or the class tomorrow. Or you
Yeah.
can ask them to come read a paper and come.
Well, we have all the reading. So I have a quick question. How many of you have been reading any of the papers that I've been putting up? Yes. 1, 2, 3, 4, 5. Oh no, that was okay, 4. Don't keep putting up your hands. So I would.
You would say you have to read this specific paper tomorrow, and then probably.
So the module for this. Okay. So the course syllabus for today has a collection of papers. We've covered 2 of them already. It's on the web page for the course. You didn't send the. Did you not?
You have sent it? You can't see that. No, he has on our website. We sent a link to all the participants, including me. So, faculty members are a little lazy.
Yeah.
They tend to see their
Did
own
you
website.
get your student to read the email and tell you the thing? Yeah. So
Comprehensive. Not comprehensive in the fairness sense, but
Yes, it's very biased, all my papers on there. So, no, but I think that would be also helpful. I think some of these ideas are very technical and very arcane, and if you read the paper, even if you don't understand everything, it's... So I would suggest that, take a look at so the papers, so today is December 13th, right? 13th? Yeah, okay. So the December 13th section of the syllabus has a bunch of readings. We've covered 2 of those papers already. The first paper on modifying Y and the second paper on modifying X. This is in the section of detecting and pre-processing the input. There's a whole section on how to build a better classifier. There's a bunch of papers there. Take a look at least the first few of those. I'm going to go through them tomorrow. So.